Welcome, my dear NEET warriors, for the next yet amazing session of your class 12 electrostatics. And today we are going to see electric potential and energy. Last lecture, if you remember, on our channel. Hello, hello. Am I audible now? Am I audible? Am I audible to all of you? Please let me know quickly in the chat box. Am I audible? Okay, perfect. So, welcome aboard to the next yet amazing session of your electrostatics and charges. A big chapter, interesting chapter, a lot of dependencies and a lot of marks to score. So, last lecture we have completed electric fields due to charges. And if you have not seen that, please check it out and smash that like button out there. And after every class, I want all your answers in the comments of the homework question. Really disappointed to see very few people solving it. Those people who are seeing are enjoying the class. And when is the next class? Well, every time 8 o'clock is 12 standard, 6 o'clock is 11. Today we had to shift the timing because of some other class which you are priorly engaged. Okay. So otherwise 8 o'clock we are going to start our 12 standard classes. So let's begin with your Captain Shreyas, your physics master teacher. Smash that like button, mark your attendance now. Yeah, go ahead, mark it right away, right now. And this Saturday, that is tomorrow on 21st, we are going to celebrate all our achievers, all our toppers in the Vedantu Achievers, yes, League. Tomorrow, 6 o'clock. The session is already live on the channel, by the way. You might have seen it. Okay, we are going to celebrate it tomorrow. Okay, so make sure you are there, right? Great. And you're going to see all the toppers. Some of them are from our DNA batch, some of them are from our pro batches, some of them are from our, offline centers. So a mixed bag of students, but majority of the students are from online, and you would definitely want to see the other side of them and all teachers coming together, at one place. It's going to be a grand event. So everybody is invited online. Cool. So let's begin with the session. And hello, Harni, Satya, Ari. Welcome, Lisa. Hello, Hari. Hello, Aparijata. Hello, RXB. Welcome, 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 everyone. Yes, sir. Units and dimensions part 2 is also coming. Yeah, the syllabus will be completed, much before, this year, but before the year end we'll complete it. Good evening, Somesh. Good evening. Smashed it yesterday only. Yes, I see some of you smashing it yesterday only. Thank you so much, guys. So before we start the concept of electrical potential energy and electrical potential, we need to understand the relation and the idea of potential energy in general and the concept of work which is related to it. Okay, so which is a 11th standard kind of revision. Without that, it is very difficult to directly jump into this particular concept. Now, from 11th standard, we know that work is nothing but, the product of force and displacement, right? Work is basically how the process in which the energy gets transferred from one body to another body. Okay, and potential energy. So just putting up the definitions right over here. So work is nothing but our force vector dot producted with our displacement vector, and it is basically how much it basically transfers the energy. Work will always transfer the energy from one place to another, from one body to another. Whereas when you talk about the concept of potential energy, it is basically the amount of stored energy. It is the amount of stored energy due to its situation or configuration, due to its configuration or situation. Like if you take a bow and arrows bow and you stretch it, because it is stretched, there is energy stored. You take a spring and you compress it, there is energy stored. You take a mass and you place it somewhere, because of its position, it has gravitational energy. Same way, charges also will possess electrical energy. We'll see in a bit. So it's a stored form of energy because of the way it is configured or arranged. One and the same thing. Okay, it's a stored form of energy. And this particular energy, different types are there: elastic, gravitational, potential energy, even spring energy is there. And today we are going to learn about electrical potential energy. Other forms can also be there. Okay, now how are these two exactly related to each other? Okay, is work and potential energy related to each other? Yes, definitely. But before going there, one more important thing, that potential energy, potential potential energy is always always measured with respect to something, is measured with respect to something called as the zero configuration, with respect to the zero energy configuration, zero energy configuration. So you assume something's energy to be zero. With respect to that, you might have some energy. Like a spring, which is not pulled or compressed, has zero potential energy stored in it. So when you pull it, it has some energy stored. So when I say the energy is 5 joules, it is 5 joules with respect to the uncompressed state. Okay, so always there is a zero energy state or zero energy configuration. So with respect to which you measure the potential energy, with respect to which you measure the potential energy. So whenever the potential energy changes, so whenever you have a change in the potential energy, for example, I take a spring and I pull it, or I take a mass and I keep it on the top of a, almirah or a table or something like that. Yeah. So then there is a change in the potential energy. Change means delta. Potential energy symbol, usually we use capital U, not small u or v. Capital U is the symbol for potential energy. This change of potential energy will come because somebody is doing work. And who does work? In that case, basically the external force, the work done by external force. So whatever is the work by the external force, what is the work done by external force, that work done by that external force is exactly equal to the change of potential energy, is exactly equal to the change of potential energy. To demonstrate this, let me give you a simple example. Imagine there is some mass over here and I take it over here. I take it over here. Okay. In this process of taking this particular mass like this and bringing it to some height, so maybe some external force did, example, 30 joules of work. If I did 30 joules of work, where will it go? It will go faithfully and get stored in the form of gravitational energy. So there will be a change of gravitational potential energy. So there will be a change of gravitational potential energy exactly of the same amount, which is 30 joules. So all this energy, all this work goes into this form of energy. Is that very, very clear? Absolutely very clear, everyone? Yeah. Thank you. Thank you, Paki, so much. Hi, Sweetie House. Hi, Satya. Yes, good evening. Uh, V is also potential energy. No, Siddiqui, I will tell you, V is for potential, not for potential energy. That confusion between potential and potential energy, today you will understand after attending my class. Okay, or else you will just know the definition. Many teachers teach the definition. I will not teach you just the definition. I'll go beyond that. I'll make you understand what is potential and potential energy. Don't worry. Okay, but that's not all. You will also hear some word called as work done by the conservative force. And always you will see potential energy is associated with elastic, gravitational, spring, electric. These kind of forces, these kind of things are conservative in nature. So comes the next concept over here, which is also useful in this chapter, which is the concept of conservative force, my dear. Okay, so when I say that we have a conservative force, conservative force, conservative force, that means if you take that particular mass or take that particular body and you bring it back to the same place, and as long as the forces are acting, there will be some work done. So in this whole process, the work done in a closed path, in a closed path will be zero. So such a force is called as conservative force. So I move a body up, maybe some gravity is doing some negative work. I bring that body down, the gravity is doing positive work. So total work done is zero. I extend a spring, some maybe negative work. I release the spring, maybe positive work by the spring force. Total work done zero. But forces like friction, normal, etc., they might not end up doing zero work. If I push a box here, the friction might suck out all the energy, will do negative work. If I push the box back to its original state, again the friction will end up doing negative work only. So it will not do zero work just because I have brought the box back to the same place. So there are some forces which do zero work when I bring it back to the same place. Some forces simply don't. So those forces which do total zero work, they are called conservative forces. Examples of them, gravitational force, spring force, electric force, all these forces, electric force, elastic force, all these forces are basically conservative forces. There is another unique property of conservative forces, and that is this: not just closed path. Imagine you go from point 1, or let's say from point A to point B via two different paths. Like this is path 1, and let's say like this is path number 2. The work done in both the paths will be the same. Yes, the work done via path 1 and the work done via path 2 will be the same. Basically, work is independent of the path. Work is independent. Work is independent. Work is independent of the path which has been taken. That is another unique property of conservative force. So forces like friction, normal, tension, normal, tension, viscous force, which is in fluids, viscous drag force, etc., are non-conservative, in nature. So they will not do zero work, and the work also depends on whether you take a shorter path or a longer path. So the work will definitely depend there. Is this much part okay, my dear students? Yeah, this is a recollection of your 11th standard topics. I didn't want to skip all these things because it is needed over here. Okay. So why did we come back to conservative force? Notice these names: gravity, spring, electric, elastic. These names are also coming over here in potential energy. It tells that potential energy can be only spoken about or can be linked or associated when there is a conservative force. Kind of makes sense because conservative, the name itself says it, conserve. So when you push it, maybe it does negative. When you leave it back, it does positive. It conserves everything. It is able to store and give it back faithfully. It's like a friend whom you can trust and give your money, and when you ask for it, he gives you back. So conserve. So capacity to store your money. Yes, potential energy is there. But maybe another person, you don't know much, you give that person some money, you ask for him, and he's like, oh, when did you give me money? Sorry, boss, no money with me. That's it, gone, lost, your money is lost. So not conserve, non-conservative, like friction. You You do some work in this way, you bring it back, like no, zero work. I am going to do some work. Okay, some positive, negative, doesn't matter, but total work done is not zero. So it cannot store, or it does not have the ability to store energy. So that is why you will see that conservative forces are only linked with potential energy. So it is always linked with conservative forces, linked with conservative forces, conservative forces. So observe over here in this particular example, where I took this particular mass from one height to another height, I pushed it up, I did some work of 30 joules. So whatever work I did got stored in it as 30 joules in energy form. In this process, gravity is acting down, my displacement is up. So force is down, displacement is opposite to the force, work done will be negative. So if you ask me, what is the work done by gravity? Work done by the gravitational force, in this case, it will be exactly minus 30 joules. You might be wondering, how did I come up with this? See, if I am doing 30, gravity is sucking away that 30. But don't worry, whatever that 30 joules it is sucking out, it's not losing it. It is faithfully storing it in its piggy bank, in its kitty. It's safely storing it in the form of potential energy. So don't get scared. The numbers are exactly matching. That means you should be happy. Yeah. If you did more work and it is not doing same work here negatively, then you should be scared. Then maybe something is being lost and maybe mismanaged here and there. So I did 30 joules. Gravity sucked away 30 joules. But don't worry, it's stored in the form of potential energy. Is that absolutely clear, everyone? Okay. Uh, don't worry, I will just mention the admin regarding the PDF, and we will definitely get it arranged. Okay. How do you know that the work done is zero? So basically, just imagine this. If I take a mass up like this, okay, gravity will do minus mgh work, minus mgh work. If I take it here, it will do zero work. If I take it back here, force and displacement in the same direction, so plus mgh. And if you take it over here, it will do zero work because force is perpendicular to displacement. So in this closed path, so work done in this particular closed path, as you can see, is zero. So you can calculate the work done in a closed path by using the definition of force dot displacement. Yeah, force dot displacement. If you do it, easily you will get the work done. Is that clear? Okay. So for conservative forces, it happens that the total work done comes out to be zero. Okay. All right. Great, great, great. Awesome. 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 Perfect. Let's go now to the next concept. Where is it? Where is it? Where is it? Yeah. So now let's go to the concept. So here it is. Work done by gravity is negative of this. So I can add to my formula over here. If work done externally is delta U, that is also equal to negative of the work done by that particular conservative force. Whatever that conservative force is, so work done by the conservative force, the negative of it is external work, which is also delta U. So this becomes a very important formula. We will block this off. We will block this off. Negative work done by conservative force is work done externally is equal to delta U. Okay. Awesome. Lisa, I think I have mentioned this in the live session itself of the DNA batch. You can check it out. Yeah, the DNA batch here and even the DNA 1.0 also. That entire syllabus will be taught by 2 to 3 teachers depending on the vastness of the subject. Like biology is a vast subject, so we have 3 teachers approx. So, because we want to make sure that the syllabus gets completed by November and December. Rather than having one teacher and giving a false promise, it's better to tell you first only that there will be 2, 3 teachers, but we will complete in detail by November, December, like we did last year. And we want to make sure that we give that quality. One teacher cannot complete the syllabus, you go anywhere, okay? Unless you have only one batch, but we have multiple batches, please understand that. Yeah. Cool. work done is 0, then it is conservative. Yes, work done is 0 for a closed path, not any time. If I go from one point to another point, work done is 0 does not mean it is conservative. Closed path, meaning I have to come back to the same place. I have to come back to the same place. That's why I mentioned closed path. Okay, is that right, Satya? Perfecto. All right. Yes, sir. So these three slides are the most important slides before you talk about potential energy and potential. So now let's talk about electrical potential energy. So now let's talk about electrical potential energy. See, imagine two charges. Imagine two charges. Imagine two charges. Okay, maybe positive and positive. They will obviously try to repel each other. They will obviously try to repel each other. It's like there is a spring over here. The spring is trying to push it back. It has some ability to do some work. It has some ability to do some work. Is that right? Yeah. No, Paki, I will not be reading NCERT in this session. I have already done it last year, NCERT line by line. So you can check those sessions in case you want the NCERT only perspective. But we are going not just NCERT, but beyond NCERT and a NEET perspective. You know, this is the lecture. It's not CBSE perspective. It is NEET plus NCERT perspective. And we have to take care of beyond NCERT also because you saw how the physics paper was this time. Okay, cool. So it feels like there is some kind of energy stored because it is able to repel and move, and hence there is some electrical potential energy stored in them. Not just for positive, positive, but even for, let's say, negative, negative also, they will repel. They will repel. It feels like a compressed spring. So it feels like you have a compressed spring over here, and you know it's trying to push it away from each other. So it feels like a compressed, feels, it's feels. Okay, this is a feeling. It's not exactly like a compressed spring. It feels like a compressed spring. Same thing I can also talk about a positive charge somewhere and a negative charge over here. Then it feels like there is an extended spring because because the things will try to come back into place. It feels like a extended spring. It feels like an extended spring because of the attractive forces. Because of the attractive forces. So this feeling is enough for me to realize that a system of charges, a system of charges, a system of charges, a system of charges possess possess put electrical potential energy. A system of charges, they will possess electrical potential energy. That is enough for me to understand. Is that right, everyone? All right. Of course, yes. Okay, perfect, Paki. Now, you might be wondering, sir, just like spring, when it is not extended, then you said that, you know, it has no potential energy. Like that for charges, what is that scenario, sir? Let me tell you. Imagine, 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 this is our entire universe. Okay, this is our entire universe. Chumma, this is a representative diagram. It is, you cannot show in universe like a circle, ellipse, whatever. Okay, say for example, one of the charges is here, another charge is here, or one of the charges here and the other charge is basically over here. So what I'm saying is that there is infinite distance between them. When there is infinite distance between them, then there is no no there is no attraction or repulsion. No attraction, no attraction or repulsion between them. And such a situation, when there is infinite separation between them, when there is infinite distance between them, then I say, because there is no attraction and repulsion, it's as if they have no energy only. So then I say that the electrical potential energy, electrical potential energy is basically big fat zero. Yes, it is basically big fat zero. So such a situation is called as our zero energy state, our zero state, a zero energy state. Remember, I just told you about zero state over here, that always potential energy is measured with respect to some zero. So that zero I have defined, that when the separation is infinite, then it is a zero state. So let me block this off for you. What is the meaning of zero state? A zero state is when you have infinite separation, then you call that as zero potential energy state. Is that absolutely clear? So everything is now measured with respect to this zero state. Everything now is measured with respect to this zero state. Okay, sir. Finally, I understood this. But there is one very interesting thing now. Observe carefully. Observe carefully. There is a common rule which you should know, that whenever something has very high potential energy versus when something has low potential energy, the system always tries to go from high potential energy to low potential energy. A best example for that, imagine you have some rock which is maybe on some hill, okay, rock on some hill. This rock has a high gravitational potential energy. So you will probably see that the rock will definitely try to fall down. It will try to fall down onto that slope somewhere. So whenever the potential energy is high, essentially the system is going to be very, very unhappy about it. But when the moment potential energy is low, you are going to be very, very happy about it. So unhappy when high energy, when you are low energy, then low potential energy, then you are very, very happy. This is very, very interesting thing which will help you decode so many questions. Okay, best example is right over here. Even for that example of spring, you can see it is valid. When you take a spring which is extended, it is really, really unhappy. But when you release it, it will come back to its natural state. It has come back to its natural state. It will be so happy and relaxed. So the lower the potential energy and you release off those things, release off the energy to the surrounding whatever, and you go to a lower energy state, you become peaceful. That is the rule of the universe. Not just for electrostatics, but also for gravity, spring, magnetic, anything, anything. Is that clear? When charges repel, then the spring should expand, na sir. So, the charges repel, the spring should expand. Where are you saying? Here, see, here, don't think exactly the spring formula. The formula for the force for spring is kx, but here it is not kx. Here it is kq1 q2 by r square. So that's why I said don't exactly make it look like a spring. That's why I said feels like. It feels like they are repelling. Oh, like a spring they are repelling. Oh, like a spring they are attracting. Okay, which is extended. Just use that part. Don't use the force formula, because then you will feel that when the separation increases, spring force will decrease, but here the force is not decreasing or increasing. What should happen? So all those things will happen. So only just take that part of understanding where that feeling of pushing away or pushing in comes at. Okay? All right. Is that okay, Siddiqui? Hi, Latika. So only that part of that feeling of repelling or pulling it inside, only that part you realize. Other formulas, other relations don't consider. Is that okay, Siddiqui and SR? Hi, Shah. Good evening, my dear students. Everybody till this point absolutely clear? Okay, sir. Yes, I understood now. So think about it. If you compare this zero state versus this state, who is more happier for repulsive charges, for repelling charges? When you are infinitely far away, you are very happy. You bring these things closer, they are becoming unhappy, guys. So if they are becoming unhappy, that means their potential energy is what? If they are becoming unhappy means what? Their potential energy is increasing. Exactly. So if this infinite separation, if this infinite separation, so U infinity is basically 0. Infinity means infinite separation. U means potential energy is 0, which we have written down over here. Can you guess what will be the electrical potential energy when they are separated by some distance? Well, 100% it should be a positive value. It should be more than 0. 100% it should be more than 0 because it should be higher than this. So 100% energy is going to be a positive value. But compare it with this. But compare this with this. When they are far away, their energy is 0. But they want to be together because they are opposite charges, attractive in nature. So they will come closer, 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 and they will stick. So they will become happier. That means their energy, imagine this number line, that will be very, very useful for all of you. Just imagine this. Okay. This was your 0. When they attract, when they repel each other, then it is a positive value. When they repel each other, their energy should fall down. It should become lower and lower than 0. So it will become negative. So the energy will be definitely lesser than this 0. So therefore, U is going to be negative in value. Therefore, U is going to be negative in value. Did you understand why for repulsive forces energy, potential energy is positive, and why for attractive charges, positive, negative, negative, positive, it is negative in nature, not formula wise, just concept wise. Cool guys till this point? Yeah. So positive, 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 negative, how it feels like, and why the energies are positive and negative. I have explained this to you. Clear? Okay, sir. Now comes the idea of, sir, what is the exact value? So the value of the potential energy is as follows. The electrical potential energy, the electrical potential energy is nothing but the work done to assemble the charges. Simply put, work done to assemble the charges from infinity. That's it. As simple as that. So just imagine this was your universe. Okay. Maybe you had one charge over here, let's say capital Q, and another charge over here, small q. Right now, the separation between them is obviously infinite separation. Eventually, what happens is slowly, you are going to bring these charges closer and closer, whatever way you want. Let's say you bring this charge here. Let's say you bring this charge over here. Okay, like this, you are bringing these charges. Okay, and you brought this charge over here at Q, and this is basically small q. So now there is some separation between them. Now there is some distance of separation between them. Let's say I call it R. Okay. So basically, by this definition, the electric potential energy of these two charges, when they are separated by some distance of R, will be equal to, what will it be equal to, guys? It will be equal to the work done by that external force from bringing the charges from infinity to that distance of R. Work done by the external forces, okay, to assemble them. Hey, please come together, because there might be some repulsion, attraction, something might be there. So you're bringing them together. So you are doing some work. So whatever work you spent will be exactly stored in those charges as electrical potential energy. Now this, after integration and all of that, the answer comes out to be K, which is Coulomb's constant. Then you have first charge, second charge, divided by the separation between them. So this is the formula for it. Is that okay? This is the pure definition. This is for two charges. This is basically potential energy of two charges. Potential energy of two charges. Is that absolutely clear, my dear? Yeah. The general definition, I have mentioned it over here. This is what it is. Electrical energy is the work done to assemble the charges from infinite separation to a finite distance or to some distance over here. Okay. Give me a thumbs up, put up a fire emoji, then we'll go ahead. Yeah. Let's maybe do a question on this. Let's do a question on this. Find the electrical potential energy of a proton and electron in an atom at a distance of 3.6 angstroms. Okay, so we have a proton, which is basically plus E, and an electron, which is basically negative E. And the separation between them is how much? 3 is basically 3.6 Armstrong. That is the separation between them. 3.6 Armstrong is 3.6 into 10 to the power minus 10, which I can also write it as 36 into 10 to the power minus 11 meters. Okay, so in terms of meters. So let's try to figure out what is the electrical potential energy. Formula wise, it is KQQ divided by R. K is basically 9 into 10 to the power 9. First charge is E. E value is 1.6 standard, 10 to the power minus 19. Next charge is negative E. So minus 1.6 into 10 to the power minus 19. The whole thing divided by the distance. Distance is 36 into 10 to the power minus 11. Okay, I can see easily that this 9 is going with this 36 4 times. So I will just keep it as it is. Okay, so we have 10 to the power 9 from here. And what is 1.6? I can write it as 16 into 10 to the power minus 20. And same thing, 16 multiplied by 10 to the power minus 20. And obviously whole thing divided by 4 into 10 to the power minus 11. Further calculations, 4 goes with 16 4 times. 16 fours are 64. 16 into 4 is nothing but 64. So this will be 64 for sure. Rest of the things, let's calculate. Okay, so this is minus 20 and minus 20. That will make it minus 40. Okay, and this minus 11 goes on the top and becomes plus 11. 9 plus 11 is basically 20. So this will become, instead of 9, this will become plus 20. In fact, I could have just done this then. If I just cancel this, this will minus 11 will go on the top, it will become plus 11. 9 plus 11 is basically 20. 20 and minus 20 will cancel. So this cancels completely with this. So I'm left with only 10 to the power negative 20. So 64 into 10 to the power minus 20 joules. That is the answer. So that is the energy between a proton and an electron. It is very, very small. It is extremely, extremely small. Direct formula application. Is that okay? So come on guys, in case you have forgotten to smash the like button, please do that right away, right now. Okay, very, very important. Do it right now. Okay. Yes, sir. Understood how to calculate the electrical potential energy. So quick recap of what we have done till now. We have said that potential energy is the stored form of energy, and this energy can be stored by some person doing some work externally. If I do 100 joules work, all that energy will get stored. And this energy is only associated with conservative forces like electric, gravitational, etc. And conservative forces basically try to conserve the energy. And if you bring it back to the same place, the total work done is zero. Not individual work, total work done is zero. And that will exactly be negative of the work done by the conservative force. So if change of the energy is 30, external will also be 30, but gravity will be negative 30. Only this part will be negative, these two are positive. If this is negative, this will be positive. Okay, the sign will change. So then we saw that, okay, if you have two charges, they will store some energy between them. When there is infinite separation, no energy stored between them. So the energy stored between them can be positive or negative, and the formula between them is KQQ by R. Notice how if both the signs are positive, 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 or if both the signs are negative, 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 the multiplication becomes positive. So energy is positive, exactly like we predicted over here. But if one is positive, other one is negative, then the entire number will become negative, just like we predicted over here. So this is a very sign sensitive equation. Don't just take magnitudes, take the sign also. Okay, please take the sign also. Yes, perfecto. Awesome. Okay, very good. So yes, 64 into 10 to the power minus 20. Yes, Satya, perfecto, perky. Let's go now to the concept of potential. Let's go to the concept of potential. So imagine a Pandu or a Champa. Okay, imagine a Pandu or a Champa. Let's say this is a Champa, and this Champa is thinking or very confused. Can I crack NEET? Okay, she's very confused. Can I crack NEET? She's scratching her head. Okay, so she basically, studies really hard. Okay, she studies really hard. She comes in contact with some books. Okay, some nice books, a nice batch, a nice teacher, everything, all the things, maybe test series, okay, whatever, everything, a combo package. And after that, as a result, what happens is that Champa now, that same Champa will be very happy. She will be celebrating her victory. Okay, she will be celebrating her victory, and maybe she will be in the Ames College. Yeah, she's in the Ames College. Yes. So as a result of all of these things, she is now in the Ames College. Does that matter whether Champa scored 60% in boards, or Champa took fifth drop, or Champa is a fresher, or Champa is not confident? Doesn't matter. It doesn't really matter. So Champa had ability to crack. She had ability to crack. Ability to crack. With the other things, with the right resources, or with those other things which are needed, she was able to crack it, and she was able to get in to the Ames College. She was able to, conquer it. She was able to conquer it. Same thing is also with charges. Same thing is also with charges, guys. So imagine there is a charge. Imagine there is a charge, and you are at some distance from the charge. Does the charge have ability to get energy? Some other charge have ability to get energy if it is placed here. That is basically called as potential. Is there potential at this particular point? Is there potential at this particular point? The answer is yes. If you bring some other charge, over here, and you place it over here, then obviously it will conquer it, and what it will have as a whole, I mean, this original charge is there, and that other charge is also here. So now together they have potential energy. So now they have potential energy. Yes, same way, just like over here, they have conquered it and they have got it. You have got it finally. You have achieved it. So potential is basically, do you have the ability? It's not that you actually have done it. Do you have the chance, ability, right, to gain energy if you place some other charge over there? That is basically the idea of the word potential. That is basically the idea of the word potential. Is that absolutely clear, everyone? Very good. So the manner in which we define potential is, maybe there are many charges here, plus, minus, plus, anything, and maybe you are standing at some distance r from it over here. This is the point under question. This is the point under, scrutiny. I am wondering whether this guy has potential over here. Do you have potential or not? So what will you do? You will be like, yeah, I have potential. How do you know that? Well, the manner in which I define potential, potential, electric potential is nothing but you do some work, in bringing a test positive charge, from infinity to that particular point, infinity to that particular point, this point over here, to this particular point over here, and you divide it by the value of the test charge, by the value of that test charge. That answer will be the electric potential. That answer will be electric potential. So electric potential symbol is capital V. It is not small v, it is capital V. Is the work done, in bringing an test charge from infinity to that particular distance r, and the whole thing divided by the test charge which has been brought, divided by the test charge which has been brought over there. Yeah, that is the true definition of electric potential. So maybe this was our test charge, q test, and I will come from infinity, which is the end of the universe. Slowly, I'll bring this charge and I will put it over here. So whatever will be the work done per unit charge, that will be the electric potential. Why do I need a test charge? Because how will I test whether it has energy? So when Champa asked, do I have ability to crack NEET? So you're like, okay, here is the test. Champa passed the test. You're like, okay, Champa, in this small test, you have achieved this much. So definitely you have potential. So usually the test charge is very, very small and you bring a positive charge only. Reason is you cannot, then there will be a confusion. I mean, one person will get positive charge, he will get negative answer. Another person will get positive charge, he will have different sign of answer. So the test should be standard. One person is giving easy paper, person is giving difficult paper. One person has no negative marking, one person has negative marking. So that will not be correct. So you should have a standard test. So we said, let's make positive as a standard. So only if you bring a positive test charge, then I can say that the test is standard. And then I can define electric potential. Is that absolutely clear? Okay. Yeah. Awesome. Okay. Yeah. We forgot the negative sign in the previous thing. I'm so sorry. You're right. There was a negative sign over here. We forgot that. So sorry. Minus 1.6 minus. Yeah. The energy was negative 64 into 10 to the power minus 20 joules. So sorry. Please correct it. Thank you so much for pointing it out. Okay. Now, if you ask me, is electric potential a scalar or a vector? Well, it is obvious that work done, charge, everything are scalar. So it is a scalar quantity. Also, if you ask me what is the SI unit of it, you can see joules is there on the top and there is coulomb over here, that has been given a new name. It is called as a volt. It is a volt. So a volt is when you do 1 joule of work to bring 1 coulomb of charge from infinity to this point. A volt is when you do a joule of work in bringing a coulomb of charge. Is that right? Okay. Now potential, you cannot give any 3D examples. The reason being, potential does not have direction, vectors. Yeah, it's a scalar. So that is the reason why there is no animation or simulation for energy. But for field, force, etc., we had nice simulations, isn't it? So you have to feel the potential, you have to feel the energy within you for understanding it. So that's why I gave you the examples of Pandu Champa so that you guys get some, feeling of it. Okay. So, sir, is there, okay. So, sir, is there a formula for electric potential due to a point charge? due to a point charge? Yes. Say for example, there is a charge capital Q over here, and at this particular distance r, at this particular point, I'm interested in what is the potential. So I again take my small test positive charge, small test positive charge. I will bring it from the boundaries of the universe, which is infinite distance. Slowly, I will bring it over here, and that's how I'll measure the potential. So potential will be the work done to bring it from infinity to that point, whole thing divided by our small test charge. Now, this answer will come out to be K. Remember, it was Q by R for energy. That Q will get divided actually, it will get cancelled. You will see that it will be just KQ divided by K capital Q, K capital Q divided by small r. That's it. That is the answer for electric potential at a point. That is the answer for the electric potential at a point. If you ask me how will the graph look like, see, very interesting. This is basically your distance from the charge, which is small r, this is 0, versus electric potential. If this capital Q is positive, you can see capital Q is positive, the answer will be positive, and voltage is inversely related to R. If it is inversely related, it will be basically like this. Yeah. And if the charge is negative, you can see Q is negative, V will be also negative, then the graph will be like this. So this is for negative capital Q, and this is basically for positive capital Q, positive value of capital Q. But both the places, one thing is common, voltage is inversely proportional to R, and whenever things are inversely related to the power 1, R's power is 1, then these curves are, this curve is a hyperbola. In fact, more specifically, a rectangular hyperbola. Rectangular hyperbola. Very, very important. This curve that you see is a rectangular hyperbola. Is that clear? Okay. See you soon, Paki. No problem. All right, Pratibha, sir, remember me. Thank you very much. NEET exam, because of you, I cleared category rank 250. Wow, really? And that is too good, yeah, Pratibha. And I'm so glad. I'm pretty sure you're going to get a good college now this year. Hope to hear back from you within a couple of weeks after the rounds are over. No more NEET exam for you, I believe. Proud of you, Pratibha, and do message me. In fact, tomorrow we are going to celebrate all our rankers. And if you have studied, I mean, we don't mind booking the air tickets for you at the function. We can book the air tickets for you, your family, your parents. You all can come down. We can book a hotel for all of you. There are around 100, 200 students who are coming down just tomorrow, flying from different parts of the country. NEET JEE toppers. We would love to have you. Yeah, if possible, just get in touch. We can book it ASAP, and hopefully you will be here. Yeah, congratulations. Sir, why for volt and potential energy radius is only R and not R square? Siddiqui, what happens is when you see the derivation, things become very clear. Work done, right? If you see, energy is basically, it's not radius, by the way. R is not radius, R is distance. Don't confuse, okay? R is not radius. Be very, very careful. Yes, sir. No problem. Even if you have studied from YouTube, we still are very grateful. See, guys, we don't differentiate like that. If you have studied from us, we are very happy. Okay? Yeah, doesn't matter. See, R is not radius, number one. Number two thing, this is work. Work is what? Force into displacement. So when you actually try to do that work, calculation from infinity to R, work is integration of force and displacement. And force is basically Q divided by R square, and displacement is basically small dr. So this will become K, Q, Q, and this is R raised to minus 2 dr. So when you use the formula, this integration, what is this integration going to be? Just think about it. The integration will be R raised to minus 2 plus 1 by minus 2 plus 1, which is R raised to minus 1 by minus 1, which is minus 1 by R. So that R comes because of that integration. So that is the reason why for potential energy also you will see R below, and same thing even for electric potential also you will see R is there below. Is that okay? Clear now? Perfect. Okay. So let's see a question. The value of electric potential at 9 centimeters from a point is how much? This was in the NEET exam last year. So let's see how to solve this. So we have a charge of 4 into 10 to the power minus 7 coulomb, and you are at a distance of 9 centimeters from it, and at this particular point there is some electric potential. So the value of electric potential is KQ divided by R. K is 9 into 10 to the power 9. Okay. Q is 4 into 10 to the power minus 7. And 9 centimeter is 9 into 10 to the power negative 2. Is that right? Everybody with me? So what happens over here? 9 and 9 will cancel. Only that number 4 is remaining. 10 to the power 9 and 10 to the power minus 7 will make it 10 to the power 2, and 10 to the power minus 2 is here. So this will become 4 into 10 to the power 2 and 10 to the power 2 on the top, because negative power will become positive. So it will become 4 into 10 to the power 4. What is it? Volts. So 4 into 10 to the power 4 volts will be the answer, which is option D. Is that okay? Perfect. Direct formula. KQ by R. Don't do R square. By mistake, in exam, silly mistakes will happen. So be careful about it. Okay. Great, great. Yes, Pratibha, if you can't come down, no worries. Just at least tag me on Instagram. That would be very, very grateful. Yeah, I would be very happy to see you guys on Instagram. Yeah, many students are tagging these days. Okay, so next question. The graph of electric potential versus distance. The graph of electric potential versus distance from a point charge is parabola, hyperbola, ebola, ellipse. What is it, guys? Come on, come on, come on. What is the graph of parabola versus what is the graph of electric potential versus distance from a point charge? I just told you that the graph looks like this. Potential is inversely related, and such curves are always rectangular hyperbolas. Yeah. Only Satya for force and field. Remember last lecture we did it? Force and field. Force and field. Where is it? This one. Force and field. This lecture we have done it. So whenever you have electric forces, electric fields, only then you can do it. Okay, forces are 1 by r square, fields are also 1 by r square. Only energy and potential, you will see it is 1 by r. Okay, so this is field. Everywhere you will see 1 by r square coming over here. Is that okay, everyone? All righty. Let's go now to the next concept. Potential energy of many charges. So system of charges. So what to do when there are multiple charges? When there are multiple charges, it is very straightforward. See, imagine you have 1, 2 and 3 charges. Then what happens is, basically the total energy will be the energy of these two, energy of these two, and energy of these two. That's it. Add them, you'll get the total energy. So what if there is a fourth charge? No worries. There will be more energies. These two will also have, these two will also have, these two will also have. Sir, what if there are n charges? Then every pair you have to take. So there are many charges. Okay, you have to take all the pairs possible, guys. That's all. It's very straightforward. Okay, you have to take all the pairs possible. That's all. Is that absolutely clear? So whenever there is a potential energy of a system which needs to be calculated, all you need to do is find the sum of the potential energies of all possible, all the possible pairs of charges. Pairs of charges. As simple as that. That's it. That is the total potential energy of the system. So simple, dimple. Yeah. Okay. So we'll do a question on it. Maybe then you will get an idea. Just check it out. I think it was asked in one of the exams. I think it was a JEE question or something last year or something. Three particles each of 10 microcoulomb are placed at the corners of a triangle. Find the electrical energy of the system. Okay, triangle, right? So let's draw a triangle first. Let's draw a triangle first. Okay, the side length is 10 centimeters, which is 0.1 meter, and the charges which are placed, they are how much? 10 microcoulomb. 10 microcoulomb. 10 microcoulomb. Okay, so we want to find the total potential energy of the system. So it's basically the sum of all the potential energy pairs which can be formed. So first thing, these two, then these two and these two. But by God's grace or by luck, all the charges, all the distances are same. So we are safe over here. So if you just find K, Q, Q divided by R and multiply it 3 times, I'm done, I'm sorted. This pair and this pair, distance, the charges, everything are same. Got it? Even if the sign was different, then I need to be careful. But here even the sign is same. It's an equilateral triangle also. Okay, so K is 9 into 10 to the power 9. The charges are 10 micro. That means 10 into 10 to the power minus 6. And again 10 into 10 to the power minus 6. And the whole thing into 3. Whole thing divided by 10 centimeter, which is basically 0.1. So I can only see 9 and 3 over here. 9 and 3 are the pure numbers, which will give you 27. So what will happen now? This is 10 to the power 9. Okay, 10 to the power minus 6 and minus 6 will make it 10 to the power minus 12. There is 2 tens remaining, so 10 to the power 2, this 10 and this 10. This 0.1 goes on the top, it will become 10 to the power 1. So this is what it is. So 27 into, guys, this will be 1 plus 2 is 3, minus 12 plus 3 is minus 9, minus 9 plus 9 gone. Oh, this is it, 27 joules. So 27 joules is option A. That's perfect. That's the answer. Got it? How to solve these kind of questions? Everybody with me? So whenever you have to find the potential energy of a system, just have to add all those pairs of energies. See, sometimes you might get even this kind of question, guys, where you might have a square, and I have seen these things like there is Q over here, there is minus Q over here, there is 2Q over here, and then there is minus 2Q over here, example. Then when you try to find the energy, understand how things will work. All the sides are equal. This is A, this is A, this is A, this is A. But if you check the diagonals, which will also be needed, this diagonal or even this diagonal, both the diagonals will be root 2 times of A. Okay. So if you check this pair of charge, KQ into minus Q divided by A. Then next one minus Q and plus 2Q. So K minus Q plus 2Q. So if you want, I'll put it in brackets. Yeah, whole thing divided by plus these two, it will be K 2Q and minus 2Q, whole thing divided by A, plus this guy and this guy. So K minus 2Q and Q, whole thing divided by A. Then the diagonals. So KQ and 2Q, whole thing divided by root 2A. And lastly, these two. So K minus Q minus 2Q, whole thing divided by root 2 times of A. So that is how the expression will look like if it was a simple square. That's all, with some different values of charges. When we should subtract, when we should add the multiples of 10. See, simple. I mean, not that difficult. If you have 10 to the power minus 2 like this and 10 to the power minus 7, when this minus 7 goes on the top, it will be written down as 10 to the power plus 7. Similarly, let's say it is 10 to the power minus 3 and let's say this is 10 to the power 5. When this goes on the top, it will become 10 to the power minus 5. Always the powers in the same numerator or denominator can be added. So, just simple addition. 7 and minus 2. 7 minus 2, how much is it? It is basically 5. Minus 3 minus 5, how much will it be? Minus 5 and minus 3. If you add these two numbers, you will get minus 8. Is that clear? This is one type of calculation that you might encounter. Another type of calculation that you might get, say for example, 10 to the power 13 and 10 to the power 4. See, you can take it on the top and do it, okay? Or else, when both of them, one of them is in the numerator, one of them is in the denominator, both of them are in different places, then you will subtract them. So it is 10 to the power 13 minus 4. Yeah, that is basically 10 to the power 9. So one is numerator, one is denominator, then you will basically subtract. But if both of them are in the same numerator or denominator, you will just add these numbers. Is that absolutely clear how to do it? Okay, SR? All right, perfect. So that is why I have just taken 0.1. 0.1 is 10 to the power minus 1, 10 to the power minus 1, right? So when I take that 10 to the power minus 1 on the top, it will become 10 to the power plus 1. Okay, so denominator going in the numerator. All right. Sir, this was for energy of multiple charges. Is there something like potential due to multiple charges? 100%. Definitely. Imagine again you have charge 1, charge 2, like that. Multiple charges are there. This is the nth charge. Due to these charges, maybe at this place, you want to find what is the electric potential. Maybe you want to find what is the electric potential. So what will you do? The electric potential at this particular point, simply is the potential due to the first charge, potential due to the second charge, lastly potential due to the nth charge. You just add the potentials due to all the charges. It's nothing but the sum of potentials, due to all the charges, That's it. That is the total potential, nothing more, nothing less. You can put the formula KQ1, Q2 by, KQ by R, KQ by R, whatever you want, or whatever the formula is, just add those potentials, you will get the net potential. Please consider the sign, very important note. Yeah, signs are important. If one is positive, one is negative, yeah, it is to be added with the sign itself. Let's take an example of that. I think we have one. Yes, here. A regular hexagon has side of 0.1 meter and 5 microcoulomb charges placed on all the vertices. Find the potential at the center of the hexagon. Come on, my dears. Hi Ananya, hi Suraksha. Good evening, everyone out here. Let's do this. First of all, I want to find the potential at the center. Okay, potential at the center. It will be due to potential due to A, B, C, D, all these charges which are there. So there is a charge here, 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 there is a charge here. Due to all of them, there will be some potential at the center. So potential due to A plus potential due to B plus potential due to C, like that till potential due to F. But you know what the best part is? All the charges are same only by coincidence. This is Q, 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 this is also Q. Not just that, observe one more interesting fact. Because it is a regular hexagon, if you draw the diagonals and they intersect at the center, each part which is formed is an equilateral triangle. Yes, this is nothing but an equilateral triangle. So if this is 0.1, even this side are 0.1. So each side I can just call it R or whatever A I can call it. So this, even this, even this, even this, even this, everything is A only. So first of all, I can just say because all the distances and charges are same. So it is 6 times the potential of any one potential. So any one potential will be kq divided by A. So 1, 2, 3, 4, 5, 6. So take any guy's potential, multiply it 6 times. That will be the total potential. Potential due to A will be kq by R. R is nothing but A. So substitute 6 into 9 into 10 to the power 9. That's the value of Coulomb's constant. Charge is how much? 5 micro. So 5 into 10 to the power negative 6. Whole thing divided by A, which is 0.1 meter. Okay. So let's see, what do we do now? All right. So 5, 9 fives are basically 45. 45 into 6 we need to do, or you can just do 9 6 are and then into 5, one and the same thing. So 9 fives are 45. 45 into 6, guys. So 45 into 6, guys. Yeah, 4 6 are 24. So 240. And what is it? Yeah, 5 6 are 30. So just check it out. 270. Is it 270? So 9 5s are 45, and this will be 270. Just check it out, my dear students. Everybody with me? Yeah, perfect. All right. Now regarding the powers, this is 10 to the power 9 as it is, 10 to the power minus 6 as it is. Point 1 is 10 to the power negative 1, goes on the top, becomes positive 1. So 9 plus 1 is 10. 10 minus 6 is 4. So this will be 270 into 10 to the power 4. 270 into 10 to the power 4. That is the answer. Everybody with me? Understood? Clear? Absolutely. But this will be in volts. Huh? This will be in volts. That is how it is. Yep. Correct. Shall we go to the next one? Last sum I took QQ. Here I took only Q. Very good. See, in the previous problem, look at the question. Look at the question. What was the question? Electrical potential energy. Energy. When energy word is used, KQQ will come. But in this problem, the word which is used is potential. So when potential is there, only KQ will come. So look at that formula, that will give you that confidence. Yeah. Electric potential is K single Q by R, because you divide it by small q. So that small q gets cancelled. Think of it like that. And when you talk about potential energy, it is KQQ by R. For energy, you need two charges, remember. But for potential, you just calculate due to a charge, due to individual charges. So that's why you do not have two charges in the numerator. You have a single charge. Is that clear? Okay, very good. Cool. Let's go then. Yep. Now let's go to the final aspects, which is potential surfaces and all of that. So if you ask me, I just take a, say for example, a positive charge, and let's say a negative charge over here. And if I ask me, what is the locus of all the points? Locus means the collection, the set, okay, of all the points where the potentials are same. That becomes an equipotential surface. So equipotential surface is nothing but the set of all the points with same potential, with the same, right, with the same potential, with the same potential. So say for example, over here, if you take the positive charge like this, any distance r you go from the charge, kq by r, the potential will be same. So all these places, have the same potential. Chumma, let me put some value over here, maybe plus 70 volts. Chumma, I have put some value. If you go at some other distance, slightly far away, at all these places, R is same, potential will be same. Potential is a scalar quantity. So at all these places, again, the potential will be also same. So maybe the potential over here is maybe plus 60 volts. If you go a little bit further, potential will be even different, but it will be same around a circle. So maybe I can go here like this. So maybe over here, this is plus 50 volts. I keep going even further, the potential will reduce drastically. Okay, I'll have to go even further like this. So maybe the potential over here is plus 40 volts. And eventually at infinity, we know when you go till infinity, it will become 0 volts at infinite distance. 0 volts at infinite distance. So this is how the equipotential surfaces or lines look like due to a point positive charge. As you go closer, it becomes more positive. As you go far away, the value becomes less positive. That is what the graph also told us just some time back. Where is it? The graph of graph of potential. Look at it. When I'm close, it is more positive. When I go far, it becomes less positive due to a point charge. At the same distance r, the potential will be the same. For a negative charge, it will all be negative values. But when I come closer, it will become more negative. And when I go far, it will become less negative. So understand, if this is minus 50 volts, this will be minus 40, and this will then become minus 30 like that. So the number will reduce, but actual value will increase because minus 30 is more than minus 50. So potential will increase. Understand that. Potential will increase as you go far away. A lot of people think, oh, it is becoming smaller. No, no, no. It is not becoming smaller. Actually, it is climbing up on the number line. This is minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5. So for positive numbers, 5 is more than 2. But for negative numbers, minus 5 is less than negative 2. Keep that in mind. Okay. So that's the play with negative numbers. So if I go back over here and show the equipotential lines for an, negative charge, this will be very small, very low voltage, very low voltage. And then the voltage will slowly start increasing as you go far away. Like this. If you put the values, maybe it is minus 50 volts, then minus 40 volts, then minus 30 volts, maybe minus 20 volts, and eventually at infinity, it will be 0 volts. So 0 volts at infinite distance. That's how it will look like. Okay, everybody clear till this point? Perfecto. Beautiful diagram to represent equipotential lines. So there is one interesting thing though about equipotential lines. Now I will add the electric field also onto it. I'll also add the electric field lines onto this diagram and see what happens. For negative charge, the electric field lines, they will converge onto the negative value like this, isn't it? That's how the field lines will look like. Here it will come out from the positive charge like this. This is how the electric field lines look like. Can you see some interesting characteristics? In fact, there are many. Look everywhere, the field is always perpendicular to the equipotential line. The field is perpendicular to the equipotential line. So this is a common trait for every single time. So you will notice some important characteristics, and that is one of them. If you have, these are equipotential lines, you will see that the electric field lines, this is the electric field lines, everywhere they will be perpendicular. They will be perpendicular to it. Very, very important property. Okay, this is the first important thing. Electric field is perpendicular to the equipotential surfaces, to equipotential surfaces or lines, equipotential lines or surfaces. This is the first important thing which you are saying. Second thing which you will see, observe carefully, electric field always goes from higher value, electric field always goes from higher value of potential to lower value. Plus 70, plus 60, plus 50, low, low, low. Electric field always grows from high potential to low potential. See over here, the thick line represented higher value because minus 20 is higher than minus 40. Minus 40 is lower, minus 20 is higher. So this is higher voltage, this is lower voltage. Electric field always goes from high voltage to low voltage. This is always going to be true. So in this situation also, I would say that this potential might be high and this potential might be low. So very important thing that the electric field lines, this is the electric field lines always go from high potential to the low potential. Another important property. Okay, so these are two important things. This is point 1, this is point 2. Point number 3, very, very important, guys. Point number 3, remember, at some places the field will be very strong, at some places the field will be very, very weak. Yeah, we have seen that before also. At some places the field will be very strong and some places it will be weak. So here you have a weak field and here you have a stronger field, You will see that here the potential lines will be very far away, and as you come close, the potential lines will be closely spaced. Here potential changes faster, changes slower, but here potential will change very, very fast. Potential will change very, very fast. In fact, it so happens that if there is some region where there is no electric field at all, imagine there is some region where there is no electric field, then there is no reason for the potential to change, because when the field becomes weaker, potential doesn't change so fast, it is slow to change. Imagine the field is so weak that it is zero, so the potential will be changing so slowly, it's practically not changing. So I can say that the potential will be constant. The potential will be constant in this region. Everywhere the potential will be the same. Is that absolutely clear? So where the field is strong, potential will change tuck, 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 tuck. Where the field is weak, the potential will change slowly. It takes a lot of time. Okay, very, very important properties that you are seeing. Some more equipotential lines, like for a positive charge, we already saw it. The purple ones are the field, the red dotted ones are the potentials. Imagine a uniform field was there. Uniform field means electric field lines are parallel. If you draw perpendicular to the parallel lines, the perpendicular will be a plane surface like this. Yeah, the blue surface is a equipotential surface. All these points have the same value of voltage. All these points have some new voltage, but same value. Same voltage everywhere. But this point, this point, this point, all have different voltages. Okay? Everyone till this point absolutely clear? Okay. Now, let's talk about another interesting aspect about equipotential lines. Imagine I have some equipotential line like this. Chumma, I have taken some equipotential lines. Okay. This is V1. This is, let's say, V2. Chumma, I have taken something. Okay. If you take a charge, if you take a charge and you make it go along an equipotential line, if you make it go along an equipotential line like this, then you will see, if you take a charge and make it go along an equipotential line, the potential will never change of that charge. So there will be no work which you will need to do. Think of this, like a hill which has some gradient, some highs and lows. If you find a path on that hill which is at the same altitude, then you are neither increasing your energy nor decreasing. So no work done gravitation wise. So, work done to move a charge along an equipotential line, along equipotential line is always going to be zero, is always going to be zero. A very, very important thing. Okay, no work will be done. But somebody decides to take a charge from here, some path, and bring it over here. Doesn't matter. So if a charge small q is taken from an equipotential line V1 to V2, then work is done by that external force, and the formula for that is as follows. If you take the charge from one potential to another potential, 100% work is done. What is that work done? Observe it carefully, guys. The work done by that external force. Remember, at the start of the class, I gave you this right over here, is delta U, isn't it? Is nothing but delta U. So going back over here, work external will be nothing but is equal to delta U, the change of potential energy. This is nothing but change in potential energy, but the change in potential energy is nothing but charge multiplied by the voltage difference. Charge multiplied by voltage difference. Why so? Because voltage was always work per charge. So if you multiply by charge, charge and charge cancels, you will get work done, which is the energy change. That is the concept for it. Going back again, in case you are still confused, go back to the definition of potential. Here it is. Potential. It was work done per unit charge. Work done per unit charge. Work done per unit charge. Joules per coulomb. If you multiply this with a coulomb, coulomb will cancel. You will get joule, which is the work done. And what is the work done? The work done is exactly the energy, potential energy. So that is the reason why this formula works. That is the reason why this particular formula will work. Where is it? Work done is Q delta V. Work done is Q delta V. Is this absolutely clear? Everybody with me? Perfect. Amazing. Amazing. Very good. Very good. Just one second. I need to ask my another class timing to be changed. Okay. Very important. And undoubtedly, this whole thing is also equal to negative of the work done by conservative force, which is in this case our electric force. This thing I gave it to you again at the start only. Minus work done by conservative force. Conservative force is our electric force in this case. So that is why that negative sign will come. Okay. So we can definitely say that. So this is a very important formula, useful in many places throughout the physics. Throughout the physics. Okay. So we'll block this and keep. All right. Okay. So that is the concept of potential energy and potential and how they are related to each other. So one such example you might have seen that you take a charge, small q, maybe at rest, and then after some time that same charge will get some speed, okay, and you say that earlier it was on some potential line, let's say V1, now it is on some new potential line, let's say it is V2. Maybe this was high potential, this was low potential. So because the potential drops, the kinetic energy will increase. That's how you can look at it. So there is some potential drop which is there, which will be V2 minus V1, which you can call it as delta V. So since the potential drops, that means the potential energy reduces. That means the kinetic energy increases. That's the reason why the speed also increases. That's why the speed also increases. So can I then say that the loss of potential energy is equal to the gain of the kinetic energy, gain of the kinetic energy, the gain of the kinetic energy of that particle? So what is the loss of the potential energy? Change in potential energy is charge into voltage difference, is nothing but charge into voltage difference. What is the gain of kinetic energy? It will be half mv square minus 0 because it was at rest before. So using this, you can quickly notice that v square will be 2 goes on the top, m comes below, and you still have q and delta v over here. So therefore, what will be the speed of the particle? The speed of the particle will be root of, check this out, root of, you will have 2 by m over here and q and delta v. So this is what you will get if you solve this particular equation. This is the speed of the particle. The speed of the particle, the speed after its acceleration, Why? Because acceleration, because the speed is changed, speed is increased through 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 potential difference, through potential difference of delta V, through potential difference of delta V. So this formula, you will see it even in modern physics, by the way. Okay, very, very important. So with this, let's start doing a question on this. Okay, first question, NEET 2022. What is the angle between the electric force and equipotential surfaces? Thank you, Aditya, so much. Hello, Ramesh. Yes, SR. All right, Siddiqui, let's go. Come on, my dear students. Yeah, this is very straightforward. I just told you, I gave you the answer, hint, everything over here. Always the electric field lines are at 90 degrees with the equipotential lines, isn't it? I just told you over here and I showed you the examples also, how field lines are always perpendicular. So hence the answer to this will be option C. Everybody spam the answer. Very good, Siddiqui. Perfecto. Moving on to the next one on your screen. How would the equipotential surfaces look like for two positive charges placed at some distance? For solving such questions, right, just show the field lines. Just show the field lines, things will become very obvious. The field will look something like this. The field will look something like this. This is how the field will look like. This is how the field will look like. So equipotential surfaces should be perpendicular everywhere. So probably something like this, then probably after this, so it will become very, very weird. like this, maybe here also like this, and more such equipotential surfaces like that. It's a little difficult to draw, but I'm trying my best. Like that. This is how the equipotential surfaces will look like. So a much better diagram has been drawn over here. Yeah. So it will be like two concentric circles and then they will merge. Yeah, there will be circles and then they will merge as if the cells are getting divided, right, in biology. Okay, so that's how it will look like. Perfect, perfect. Let's take another example coming up on your screen. Here it is. If you take a -2 microcoulomb charge, moved from this voltage to this voltage, find the change in the energy work done by force and work done by external force. Perfect. So the concept is you are taking it from 10 volts to -20 volts. This particular charge of how much coulomb? -2 microcoulomb from here to here. Okay. Question is, what is the work done by everything, force, everything? Okay. So first things first, guys, what is the value of delta U? It is charge into voltage difference. What is the charge? It is -2 micro. Micro, I will just keep it as it is for now. Voltage difference means high minus low. Final minus initial. Okay. Final is basically -20 minus initial. What is initial? It is 10. So always final minus initial has to be done. Keep that in mind. So this will become -2 micro. -20 minus 10 is -30. Negative negative will become positive. 2 3s are 6. So it will become 60 microjoules. 60 microjoules. That is the change of potential energy. That is the change of electric potential energy. Direct use formula. Do not play with signs. Use the signs as it is. Voltage difference is final minus initial. Now comes the next part. Whatever is the change of potential energy will also be the work done by external force, that is standard. What will be the external forces work done? So that answer is also done, work done by external force. The only problem is with work done by electric force, which is conservative in nature. It will be negative of delta U, or you can just say this negative is delta U. So delta U is 60 microjoules. So minus work done by electric force is 60 microjoules. So work done by electric force will be -60 microjoules. Will be -60 microjoules. Is that clear? Understood? Perfecto, everyone, how to do this question? Direct application of formula. Which formula? We just use this formula over here. Charge into voltage is energy. That is also work done. But electric forces work done will be negative. So just shift that negative sign over there. Immediately you will get the answer. Is that okay? Perfecto. Let's go to another question, guys, coming up on your screen. A charge of mass 2 grams and 8 microcoulomb is accelerated by 200 volts. Find the speed. Find the speed. Find the speed. This is exactly like this particular theory. A charge is accelerated by some voltage. Find the speed. Use this formula. V is root of 2q delta V by m. That's it. That's it. So let's use that formula. V, speed is root of 2q delta V divided by the mass. Okay, so what is the charge? Charge is 8 micro, so 8 into 10 to the power minus 6. Voltage 200, mass that is 2 grams, so 2 into 10 to the power minus 3. Okay, a lot of things will get cancelled, like 2 and 2. Okay, 8 2s are 16, that's all I can do. 8 into 2 is basically 16. 10 to the power minus 6 is there, 10 to the power 2 is there, and minus 3 goes on the top, becomes 10 to the power plus 3. Root of 16 is 4, and over here 2 plus 3 is 5, minus 6 minus plus 5, minus 6 plus 5 is 10 to the power minus 1, which is 4 by root of 10. That's it. 4 by root 10. meters per second is the answer. 4 by root 10 is the answer, guys. Very straightforward. Is that clear, everyone? Cool. Perfect. All right. Let's go now to the next concept. This is the last concept. Just some time back, I told you, whenever field goes, it goes from high voltage to low voltage. And wherever the field is strong, the potentials change faster. Correct? Where the field is strong, potentials will change faster. Where the field is weak, potential will change slowly, coolly, aram se. Okay. So there is a formula relating field and potential. This is very, very important. See, for small changes, I can say that the work done by our conservative force with a negative sign will be a small change in the potential energy. Work done by conservative force is the conservative force itself into the displacement, let's say dr. So, oops, I shouldn't have put minus du. So sorry. This is just plus du. Yeah. Work done by conservative force will be du with a negative sign. How did I get it? Since we know negative work done by conservative force is change in the potential energy. This was for a big change. For a small change, it will be minus dw. This will be du. Instead of delta, it will become du. Okay. So now what I will do, I will take both LHS and RHS and I will divide it with, I will take, instead of conservative force, I will take that electric force and I will divide it with a test charge. Here this will be dr and this will be also energy change by dr. Now you might be wondering, why did I do this? Oh, sorry, not dr, by charge test. See, one thing is clear. Force per charge is nothing but electric field. So it is nothing but our electric field. Force per charge is electric field into our distance. And what is this? Energy per charge. Energy per charge is voltage difference. How? I just showed it over here. See this. If I take Q here, energy change per charge is the voltage difference. Is that right? Because delta U is Q delta V because of that fact. So going back over here, the logic is, since delta U is Q delta V, therefore du is Q dV. So therefore du by Q will be also dV. So that is the logic for this. Perfect. I have found whatever I wanted. That means the electric field is, take that negative sign over there, dV by dr. This is a very, very important formula. Electric field is negative dV by dr. In this formula, this dV by dr is called as the word potential gradient. Potential gradient. Potential gradient. It is basically how many volts per meter are there. Volts. How many volts are there per meter? How many voltages difference is there per meter? That is potential gradient. So negative gradient of the voltage is electric field. This is a very, very important formula. E is minus dV by dr. So let's see some questions based on that. You can have a question like this. Imagine voltage is x cube volts. Find field at x equals to 2 meters. Chumma, some random question I have taken. How do we do this? I'll tell you what. Observe. Field is asked, potential is given. So usual formula is dV by dr, negative. But here r, which is basically representing distance, and dr is basically displacement. So the displacement, everything should happen in the x-axis because all the expression is completely in x. So instead of dr, it is always better to put dx. If this was y, I will put y. If this was z, I will put z. Simple. I have put dx because everything is happening in x direction, nothing in y. So why will I waste my energy? Okay. So negative d by dx. What is the voltage? Voltage is basically x cube. Oh, derivative, sir. I know derivative of x cube is 3x square. Is 3x square. Perfect. So the answer for the electric field is minus 3x square. But they have asked at x equals to 2. X equals to 2. So put minus 3. X is basically 2. So 2 square is 4. 4 3s are 12. So minus 12 newtons per coulomb. That is the answer. So the electric field at x equals to 2 is minus 12 newtons per coulomb. That's how simple the questions are. Okay? Very, very straightforward. I'll give you more examples so that you guys are convinced more. Imagine the voltage is chumma something like 5 log x plus 4 volts. Okay? Question is find electric field. Chumma, I put something. So how do we solve this question? Again, electric field. Here, everything is in x, so minus the dv by dx. But here, voltage itself is 5 log of x plus 4. Use addition rule and all of that. 5 is a constant, so comes outside. So 5 times of the derivative of log of x minus d by dx of the number 4. That's all. 4 will come separate. 5 log x will come separate. 5 being a constant comes outside. Okay. So this will become minus 5. What is log x's derivative? It is 1 by x. What is a constant's derivative? It is 0. So hence the answer will be minus 5 by x. The answer will be Newton per coulomb. That is the electric field. Minus 5 by x Newton per coulomb. Simple. Just have to take derivative and put a minus sign. Wow, sir, this is so cool. But sir, I have a problem. What if x and y both are there? Imagine it is x square plus y cube, okay, minus z. Or okay, for now, just let's put x square plus y cube. What to do now, sir? What to do now, sir? Okay, I'll tell you what. Find negative dv by dx, but that will be electric field in x-axis. Find negative dv but with respect to y, that will give you electric field in y-axis. Oh, so differentiating with separate variables, that will give me the field in that direction. So when I differentiate with x, other things are constants. So when I do this and put x square plus y square, same thing over here, negative d by dy, x square plus y cube. Okay, sorry, this is not y square, this is y cube. Okay, what will happen? Y is going to be a constant. Please understand that when I'm differentiating with x. Yes, so when I do that over here, y is taken as a constant because I'm differentiating with x. When I'm differentiating with y, x is taken as a constant. Now solve the question, it will look very easy. Derivative of x square is nothing but 2x. Y being a constant, derivative will be 0. So this will be minus 2x. Here, x is a constant, so this is 0. And y cube's derivative will be 3y square. So hence the answer will be minus 3y square. So this is EY and this is EX. So we get components separately. That's all. So if you ask me the total electric field, the x component being 2x, I'll put I cap. The y component being 3y square, I will put j cap over here. That's all. That's how you solve the questions when x, y, z are there. Differentiate separately and then give the answer. Okay? Everybody clear about this? Say for example, it was voltage is x, y square, z cube. Chumma, taken some another example. What to do? Find x component, which is dv by dx with a negative sign. So it will be derivative with respect to x of x, y square, z cube. Everything except x is a constant, so y square and z cube will come outside. So it will be just dx by dx. Dx by dx is 1. So it will be y square by z, y square into z cube. Same thing for y component, derivative with respect to y. So it will be derivative of x y square, let's say z cube, everything except y outside. So sorry, there was a minus sign here. I just forgot to put it. So minus x and z cube will come. Derivative of y square, that's all. Derivative of y square is 2y. So minus 2xz cube, and there will be y over here. So 2y has come. Same thing, Ez is minus dv by dz. So negative d by dz of x y square z cube, except for z, everything put it outside. So minus x and y square will be outside. So just take the derivative of z cube. Derivative of z cube, 3 comes outside, minus is there, x y square will be there, z cube's derivative will be 3z square. So that's what it is. So this is x, this is y, and this is z component. That's all. Okay, beautiful question. One last thing before we wind up the class. In a certain region of volume, the potential is found to be continuously 5 volts. What is the field in this region? Very laddu question. Just some time back, I told you some properties. Where did it go? Somewhere over here. If in a region, voltage is constant, that means potential is not changing only. So everywhere the field is 0. Yeah, just some time back I told you. Just use that idea and you will get the answer. Hence, the answer is 0, because in that space, everywhere voltage is same. So you can also look at it formula wise. If voltage is constant, dV by dr will be 0. So minus dV by dr will be 0. Therefore, electric field will be 0, because this formula is there. E is minus dV by dr. Yeah, straightforward. Okay. This is your homework question. X, Y, Z is there. Find the field. Okay. Just find X separately, Y separately, Z separately. Immediately you can find the magnitude. I want every student watching this live or recorded posting the answer in the comment section. Solution, everything is there on the next slide. Okay. PDF you can download after the class is over. All right. Cool. So let's call it off a day. Thank you so much, guys, for attending the class. Make sure you're liking the video, commenting the answers, and subscribe to the Vedantu NEET English. Bye bye. Take care. This was your Captain Shreyas.